All right, workshop students, let's see if this one will help you. Again, more rotation. Here we have a merry-go-round that is a disc with a mass of 50 kilograms and a radius of 2 meters. The child has a mass of 35.6 kilograms on the merry-go-round, halfway between the center and the edge of the disc. So keep that in mind. Halfway would be 1 meter away from the center and also 1 meter away from the rim. Initially, everything is at rest. Now, the child starts running in a clockwise direction and cause the merry-go-round to spin in a counterclockwise direction with an angular speed of 0.88 radians per second. The child is running at a speed of. Okay, so this here, since it has no other outside influences, is a conservation of angular momentum problem. That is, the initial angular momentum equals the final angular momentum. And I'm going to go ahead and put it this way, that both the merry-go-round, so I'll use M for merry-go-round and C for child, both of them are at rest. So they each have no angular momentum. I guess if I was drawing kind of a circle here, here's the disc, and maybe this block will be the child if we were looking from above. So as the child starts to run, we still have to have 0 total angular momentum. So one has to go clockwise and one has to go counterclockwise. Now, we don't have to decide that. They were told us that the child goes clockwise direction. So the child starts to run this way, making the merry-go-round the other direction. So the merry-go-round spins in a counterclockwise direction with a speed of, and they put 0.88. All right. So, like I said, the angular momentums then are equal in magnitude, opposite in direction. So let's talk about the child. The child then, if I did its angular momentum, so maybe I'll put it down here, angular momentum final of child, I'll just do an R cross P. And if I focus just on the magnitude, then this would be an R, a P, and a sine theta. So the R is the distance the child is away. That's the radius. And so we were told here that the child is halfway. So it's 1 meter from the center. So the R is 1 meter. The momentum, the linear momentum, would be the mass of the child, 35.6 times the velocity of the child. And then the angle is the angle between the radius and the direction of the velocity. And so I'm kind of assuming the child is going to be running, along a circle out here. So that's going to make 90 degrees here between the radius and the direction that they run. And so there, I guess, simplifies down to 35.6 V for the angular momentum, and I'll call it final, of the child. So that's that one. And then the angular momentum of the merry-go-round, at least in magnitude, must be this 35.6 V. And in this case, I'm going to write the angular momentum a little bit different. Instead of an R cross P, because I don't have a single point object, I have a continuously distributed object, and that's where the moment of inertia comes into play. I can go moment of inertia times its angular speed. And again, we're looking for this unknown V of the child. And that's good because we have enough information to get the moment of inertia of the disc because, I should say merry-go-round because they call it a disc and it has a mass of this and a radius of this. So the moment of inertia is 1/2 times 50 times the radius squared. And the angular speed, let me just double check that number, they said was 0.88. All right, so the unknown then is V. So 0.5 times 50 times 2 squared times 0.88. Then divide that by 35.6 and I get 2.47 for the speed, and that should be meters per second, of the child. And sure enough, that agrees with the computer's corrected answer. All right, hope that helps.